Hey guys, in this video we're going to be looking at qualitative graphs. So a lot of these are going to go with a storyline, and we're going to have two different units that we're comparing, one on the x-axis and one on the y. So we're going to try and match these graphs to the scenario that they're describing. So here's the scenario. A train pulls into a station and lets off its passengers. So the graph, if you notice, every single one is comparing speed over time. So when you think about a train pulling into the station, its speed is going to slow down all the way to 0 so that passengers can get off. So we want a graph where the speed is going down continually. So this graph says the speed is staying the same, staying the same, staying the same, and then dropping suddenly, but still not going to 0. This one, starting at a certain speed and the speed is decreasing over time, and then the speed goes all the way down to 0. So that's the one that matches our scenario. This speed goes up, decreases speed, goes up, decreases speed, goes up, decreases speed. This one is speed stays the same and in an instant goes to 0. Well, that's not very realistic for a train that actually is going to slow down. We need to see that decrease over time. A man takes a ride on a Ferris wheel. So distance from the ground over time. So this one actually looks like the motion of a Ferris wheel, but here's what this one says. Starts above the ground over time, and then notice as this circle comes back, I'm going back in time, right? I'm going back across the x-axis. That doesn't happen. Time is going to continually move forward, so we're not going to have this overlapping graph, even though that's kind of the image that we might picture when we think about a Ferris wheel. This graph is saying that we're going back in time when we go towards the ground. That's not true. So this one, we start at the ground, and that our height above ground, so I'm getting higher and higher and higher above ground. I reach a certain max height above the ground, and then I start coming closer and closer and closer to the ground, not all the way back down, and then I go up again higher from the ground, and then back down. So this one would be a better match of a Ferris wheel because I go up to that maximum height, which would be the top of the Ferris wheel. This would represent the bottom of the Ferris wheel, and then this would be me starting from ground kind of before they lift off. So this one doesn't go back on itself, so where there's no going back in time. As time moves on, my height above ground is going up, back down, back up, back down. This one does that too, but it doesn't keep going back to the same height, where a Ferris wheel, we know always the top is still always going to be the same height. So this one doesn't quite match that. And then this one, again, we have an overlap in time. So once I hit this point, I'm going back in time, which is not okay. So we don't want to see that overlap. Third one, a woman climbs a hill, at a steady pace and then starts to run down one side. Okay, so we're comparing speed to time. So she's climbing a hill at a steady pace. So steady is going to be our speed is staying constant. And then she runs, so then her speed is going to increase as she goes downhill. So this one is actually the best match. Her speed stays the same until she starts running, then her speed increases. This one, even though it looks kind of like a hill, this says she's speeding up, speeding up, speeding up, slowing down, slowing down, slowing down to a stop. That's not what's being described here. This is she's speeding up and then staying at that speed for a while. Speeding up, slowing down, speeding up. So this is the only one that really matches our scenario. A child swings on a swing. Distance from the ground over the time elapsed. So higher from the ground, back towards the ground. Higher from the ground, back towards the ground. So this one's actually very similar to the Ferris wheel. But I would actually even say that this one is probably a pretty good match because when you start swinging, your height isn't your max height, right? You get higher and higher with like each pump. So the fact that this max height is getting a little bit higher each time, this one is actually a pretty good fit for a swing. All right, got one last one of these where we're matching the scenario to the graph. A child climbs up a slide and then slides down. So again, we're looking at speed. So when you're climbing up a slide, your speed should stay pretty constant, right? You're kind of climbing at a steady rate. And then when you slide down, your speed is going to increase significantly because the slide is getting really, really fast, and then you're going to stop at the end. So let's see here. This is saying speed up, speed up, speed up, stay the same, slow down. Well, we know the slow down part doesn't really fit the slide because the slide is the fast part. And even though this models the stairs and the slide, this doesn't model the speed. Because this says constant speed up, constant speed up, constant speed up, and speed up in an instant. We know that's not really possible. And then this says slow way down. Not happening on a slide. This says our speed is constant, then drops, then speeds way up really fast, and then back down to 0. This one said our speed is constant and then slows way down. Okay, so let's think about this again. When you climb up a slide, you have a pretty steady pace going up the stairs. You stop at the top. You slide down going really fast, and then once you're at the bottom, your speed is going to slow down and you're going to stop. So this one is the one that best emulates that. Constant speed going up the stairs, you stop, get settled, you slide down so your speed increases really fast as you go down the slide, and as you get to the bottom, you're going to slow down to 0 speed, not moving anymore. All right. Okay, another kind of scenario that we're going to match to one of these graphs. Sandra starts out with $43 and feeds quarters into a slot machine. Which graph shows the amount of money left after X tries, assuming she never wins? Poor Sandra. Okay, so she starts out with $43. So her maximum of the graph should be 43. It should never go above 43. And then she's gradually losing money every time she puts money into the machine, and she's never winning. So these ones all start at 43, it looks like. So that's all good, but the ones that go above 43 are not going to work. So this one's not going to work because it's going above 43. This one's not going to work because it goes above 43. All right, this is saying she's staying at 43 the whole time. We know that's not true because every time she puts money in, she's losing. All right, so this one is, she's dropping really fast. So like after 5 tries, she's lost $5. So if you think about quarters, that's only 25 cents. So after 5 tries, even if she lost all 5, she's only lost $1.25, not $5. So this one's going to be a lot more gradual loss. So she's losing it a lot slower than she's losing it in this one. So you can also think of it after 25 tries, she's lost all $43. Well, 25 tries or 25 quarters is not the same as $43, so that's not going to be that one. So that's how you kind of tell the difference between these two, because both of them show her losing money, but how fast. So that's where we really want to look at the numbers on the graph. So A is going to be the best fit. All right, second example. Richard types for 3 minutes at a rate of 35 words per minute. He takes a 2-minute break and then types for 3 more minutes at a rate of 20 words per minute. The graphs below show time on our x-axis and number of words on the vertical axis. Which graph represents Richard's time at the typewriter? All right. So he types for 3 minutes at 35 words per minute. So every minute he should be going up 35. So every minute up 35 for the first part. Which after 3 minutes he should have typed, so if he's doing 35 per minute, for 3 minutes, let's see, 70, 105, I think that is. So at 3 minutes, he should be up at 105. Let's see. I don't know if I see. All right, so this one is actually the kind of how we missed that. So hopefully you guys kind of understood what I was doing. So at 3 minutes, he's typing 35 words per minute. So 35 words the first minute, 35 more words the second minute, so he's up to 70. And then at 3 minutes, another 35 words, so he's up at 105. So after 3 minutes, I should see 105 words. So this is actually the only graph that shows that, so that actually helped me narrow it down right away. 3 minutes at 105. So this line is 100, and it's just a little bit above that. Then he still only has 105 minutes because he takes a break. So it's still 105 words have been typed. And then he sits back down and he's typing 2 words per minute. So now he's gradually getting more. But notice this part of the graph is less steep because he's only typing 20 words per minute. So it's not growing quite as fast anymore. So D is the correct one. All right. Okay. All right. I'm going to skip over 3 and 4. I'm going to leave that one for you guys because I want to get to these next couple examples. All right. Okay, Sarah walks from her home to the store. Halfway to the store, she realizes she forgot to bring money, so she turns around, returns home, gets her money, and then walks all the way back to the store. Graph time and distance from home on the vertical axis. Okay, so we're going to sketch graph here. So this is time. And I'm going to do, and this is distance from home. All right, so when it's 0, she's at home. And then as my height of the graph increases, that means she's further away from home. Okay, so let's say, so she starts walking to the store, so she's getting further and further away from home. She's just kind of walking at a safe pace. She's getting further and further away from home. Halfway to the store, she realizes she forgot to bring some money, so she's like, at that spot, she realizes she's standing there for a second. It's not instantaneously that she turns around. So she stands there for a second. And then she returns home. So she comes closer and closer all the way back to home. Home is 0. And then she gets her money. So she's at home for a little bit getting her money. And then she goes all the way back to the store. So remember, this height, she was halfway to the store. So all the way to the store would be twice as high. So whatever this height is, I want to double it to put up here. And then she's at the store. And then we don't know how long she's at the store, so we'll just kind of end it up there. She stays at the store. Eventually, she probably comes back home, but we'll leave it at that for now. Okay, so that is a graph that would model that situation with distance from home versus time. Okay, let's do another one here. Rashid is jumping on a trampoline. Graph time on the horizontal axis and distance off the ground on the vertical axis. Okay, so time, and I'm going to put height. Okay, so 0 is he's on the trampoline, and then up in the air is every time he jumps. So when you start jumping on a trampoline, right, your height isn't very big to start, okay? So you jump, come back down to the tramp, jump up, get a little bit higher each time, jump back, get a little bit higher each time, kind of just gradually getting higher and higher over time. And then maybe if you want to show kind of the end, you could keep it going and then get smaller and smaller and smaller, or maybe you jump off. But this just kind of shows you're building a jump. So a little bit higher each time. But you do come back to 0 each time, which is just back to the trampoline surface. All right, do one last one, and then I'm going to leave number 4 for you guys. All right, number 3. Kendra is speeding along the highway and is stopped by a police officer. The officer gives her a ticket and then she continues on her way. Graph time on the horizontal axis and her speed on the vertical axis. All right, so this time instead of distance, we are graphing time versus speed. Okay, so the officer gives her a ticket because she was speeding. So initially her speed is really high. Okay, she's speeding. So whatever it is, let's say she's going along at that constant speed. Let's say it's like, I don't know, she's going 60 in a 45, something like that. So she's speeding, she's staying at 60, but it's speeding. Then she gets pulled over. Okay, so she has to slow down and stop. And she pulls over, and then she stops. So she has 0 speed while she stops, and the officer is writing her a ticket. Now, she's going to speed up again once she's on her way, but she's not going to go that fast anymore. So she's speeding up, and she's only going to go 45 this time. She's going to drive the speed limit so she doesn't get pulled over again. So this would be another graph of speed versus time. All right, I'm going to leave number 4 for you guys, but there's some good examples to help you with qualitative graphs, both matching a graph to a situation or coming up with the graph given the situation.